Okay, so we were talking about the mind map, and we have all these different techniques. You will have to decide on which technique actually makes sense in CRISP-MLQ. When it comes to supervised learning and within predictive modeling, you have classification models, shallow machine learning models, ensemble models, regression models, and black box techniques. Within black box, we have neural networks. And the greatest advantage with neural network is that it performs automated feature engineering. But the disadvantage is that you cannot interpret the results. There is no interpretation which exists. When it comes to neural networks, we have perceptron algorithm, we have already discussed, which is going to handle linearly separable boundaries. Then we also have multi-layered perceptron or artificial neural network, which is also called as a dense network. This is also called as dense network or fully connected network. And then within this, we have discussed that it handles non-linearly separable boundaries. We have also discussed about convolution neural networks. And CNN handles videos and images. We also have techniques such as fast RCNN. Again, it's a variant of CNN. Faster RCNN. And we have mass RCNN. These are the various techniques, and YOLO models. You only look once. These are the various models which we have in place. Okay, and all of these models handle object detections, detecting what is there in the image. Now we need to get into RNN. But even before that, we have activation functions. These are the various activation functions which exist. And the job of activation function is to capture the nonlinear patterns. Then we discussed about batch gradient descent, stochastic gradient descent, and mini batch SGD. That is, these are the three that we have spoken about. I would say these are the techniques which are used to reduce the loss or cost. There is a difference between loss function, cost function, and error function. Then we have a lot of regularization techniques in which we discussed about data augmentation and dropout and batch normalization. When it comes to error functions, we discussed that when output variable is categorical, and there is a sheet which we have. I'll go to that sheet and we'll talk. This happens to be the sheet. Okay, and if your output variable is continuous, for model evaluation purpose, for accuracy or error purpose, we can use any of these error measures, which we will talk about in detail during forecasting. And for optimization purpose, you can use any of these. In the output layer, you'll have a single neuron, and the activation function would be linear or identity function. If you have your output variable, which is discrete in two categories, then we proceed further with binary cross entropy. Okay, when we have, you're going to have one or two neurons in your output layer, and we use sigmoid or tanh activation function in the output layer. In the hidden layers, you can use any activation function of your choice, but usually people prefer ReLU activation functions. If you have your output variable, which is discrete, and if you have more than two categories, again, for model evaluation purpose, we use the same bunch of stuff. For optimization purpose, we use categorical cross entropy. And if you have a 10 class problem, for example, you'll have 10 neurons in the output layer. So I would rather change it to N, where N is number of classes. And then when it comes to the activation function, in the output layer, we have softmax. Very strange, huh? This is not appearing in the moment I remove it from this. That's okay. Let me save it. And then when you have textual data, that is when we use recurrent neural networks. So let's get into RNN and talk more about recurrent neural network. Post that, we will run the code. So let me do here. We have recurrent neural network, and here we go. So whenever you have sequence of data, you might have sequence of words, or you might have sequence of characters, alphabets, you might have sequence of sound, or you might have sequence of words. I mean, this part is called as machine translation or language translation. Machine translation or language translation. Here, if you are given text in German language, for example, and if you want to convert that into English language, if you observe carefully, it's not a word-to-word conversion. The first word in German language might be the second word in English language. Maybe the third word in German language might be the first word in English language. So the order in which the words are processed in one language and the way the output is displayed in another language would vary. That means the entire sentence should be first read or analyzed, and only then can you convert that language into another language. Only then can you convert one language into another language. We have traditional language models. When it comes to traditional language models, if you have this, for example, next word prediction problem. This is there in Gmail also. If you observe, when you start typing email, the next set of words are automatically predicted. Stocks plunged this morning despite a cut in interest rates by the Federal Reserve as Wall Street. Since you train your model on a lot of data, obviously the moment your algorithm reads these, it would say that the next word should be street. Okay, so the underlying data, usually you train your models, language-based models, on the content which you get from the news channels. You might want to go to Wall Street Journal, you might want to go to Harvard Business Review, you might want to go to all the, well-known reputed magazines, and then the news channels, media hubs. And then you might want to take the text from there, and then you might want to train your model so that there are no issues. And then you also have spell checkers. For example, when you're typing and if something is incorrectly spelled, for instance, here you have minutes. They are leaving in about 15 minutes. Since this is incorrectly spelled, you might want to rectify that. Okay, your algorithm will automatically rectify that. In mobile, when you're typing something, automatically when you type, it will automatically change the spelling of that. Vernacular language, of course, it doesn't work well on that, but otherwise, he's trying to what? Find out? No, it will change this to find out. Speech recognition. When you're talking to your friend who is a theater owner, and somewhere the speech wasn't properly heard. So when you convert the speech to text, though the pronunciation of the theater owner wasn't right, or maybe he accidentally used the word unicorn, but then it will get changed to popcorn, because theater owner would say that the popcorn sales have doubled, not unicorn. By mistake, if the theater owner pronounces or uses some other word, it will automatically rectify. Automated essay grading. When you write GRE or GMAT or IELTS or TOEFL, any of the entrance exams for your higher education or otherwise, your entire essay is automatically graded. Gone are the days where, English professors used to, read and then evaluate. Gone are those days. Now, automated essay grading is in picture. Then you have machine translation, wherein you have word ordering. The cat is small. The sequence of words appearing like this will have a higher probability as opposed to small the is cat. Given this, automatically the words are ordered like that. Usage of proper words. I'm walking home after school. Walking home after school would obviously have a higher probability in comparison to walking house after school. So these are a few use cases which are solved using your language models. Let us talk about traditional language models, which we have discussed as part of text mining, wherein we discussed about word clouds, etc. Okay. And we also discussed about unigram words. Unigram words means single words. In English language, we have approximately 172,000 words, approximately 172,000 tokens or unigrams. And you can also have bigrams. When you look at bigrams, it will be approximately v raised to the power 2. Trigrams would be approximately v raised to the power 3, so on and so forth. And then if you have n-grams, the size of the vocabulary would be v raised to the power n. I forgot to do the housekeeping class. Okay. And if you want to calculate the bigram words, what is the probability that you will have word 2 given word 1? That means given the word traditional, what is the probability that next word would be language? How do you solve it? You look at number of times the word 1 and 2 appear together. That's count of word 1 and word 2 divided by count of word 1. Bigram models. Then you also have trigram models. What is the probability that you will have word 3 given that word 1 and word 2 have already appeared? So here you look at how many times word 1, 2, and 3 have appeared together divided by number of times word 1 and 2 have appeared. This would give you the probability. In this way, if we keep calculating the probability values, right, of different words, when you move from unigram to bigram to trigram, etc., the amount of compute that you need would exponentially keep increasing. There were days when people have experimented to perform probably 4 grams, etc. And this is what they found. They have taken a specific machine and they had used 140 GB of RAM and they have run it for 2.8 days. And they could build 126 billion tokens by using different engrams, right? So 4 grams, etc. they tried out. With 140 GB RAM, even today 140 GB RAM is considered to be huge. Right? It's considered to be a very powerful system. For 2.8 days. And then 126 billion tokens. Okay, so that is what, so that means you need huge amount of memory to be able to compute more than 3 grams. If you want to go with more than 3 grams, then the memory that we have might not be sufficient. This is one challenge with respect to traditional models. So let me put it here that the number of tokens would keep increasing and the size, vocabulary size will become V raised to the power N if you have N grams. If you have 10 grams, V raised to the power 10, that is 172,000 whole raised to the power 10 if you want 10 grams. Okay, next. The disadvantage with traditional language model is that, another disadvantage is that, first thing is it needs more memory or more compute output. Second disadvantage is that it will not store the previous words in memory. What does that mean? Say you're reading a specific book. Okay, and in that book, somewhere in the first sentence, it says that we are discussing the history of Spain and France. In the first paragraph. Somewhere in the last paragraph, if it says the 2 countries. Now, your traditional models do not store the previous words or the first sentence, previous words in memory. So it will not be able to correlate that the 2 countries refer to Spain and France. It would not be able to correlate in that way. Since it cannot correlate that the 2 countries refer to Spain and France, you cannot read the context. Context in the sense we are talking about Spain and France. That context will be missed. So context does not exist. I would write it as no context. Okay, next. So people thought in order to fix these traditional language model problems, can we try out neural networks? Yes, you can try out neural network algorithms. As part of neural network algorithms, they thought, okay, let us try out multi-layered perceptron. And let us see how multi-layered perceptron would help us solve the problem. Then when they started building multi-layered perceptron, they figured out that if we have 3 words and the 4th word should be predicted, for example, say you have original neural language. So you create your data set. Word 1, word 2, word 3, and then say you want to predict the 4th word. Word 1, word 2, word 3 will become 3 inputs, and you want to predict the 4th, which happens to be your output variable. This is how your data would look like. So go to Wikipedia or any other forum where you'll have grammatically correct sentences and put all the 4 words. For example, original neural language model. Original neural language model. Then go to the next part. Neural language model using. Neural language model using. Then go to the next one. Language model using MLPs. Language model using MLPs. In that way, you will have the data. And then you use those and supply it to your multi-layered perceptron. If you take a specific word, for example, you cannot supply the word as is to your neural network algorithm. For that case, images, etc. also, you cannot supply as is. What should we do then? We have to convert the categorical data. Words are nothing but discrete categorical data. You need to convert those into numbers. And one way of converting words into numbers is using one-hot encoding. So you take this word, you perform one-hot encoding. Okay, and then you'll have one-hot encoding. How would the one-hot encoding look like? Very large, because you have 172,000 words. So you'll put 1, 2, 3, 4 in that way. 172,000 words. 1, 2, 3, 4, 5. We'll have 172,000 words. For a specific word, say original is a word. You put 0, 0, 0, 0, 0. Wherever you find the word original, only there you put 1, rest all will be zeros. This would be called as one-hot encoding. And for every word that you have, you convert that word into one-hot encoding representation and then supply it to your MLP, multi-layered perceptron, supply it to the neural network algorithm. So if you have 3 words and if you're trying to predict the 4th word, you give all those 3 words as input. So all these 3 words, the size of these would be V. 172,000 words, right? You have. So the size of this would be V. The size of this also will be V. The size of this also will be V. So if you have n words, you'll have n times of V. Will be the size of this. Then you have a hidden layer. You supply all these to the hidden layer. Say which has H neurons. For example, if you have 3 neurons in your input and 2 neurons in your hidden layer, then 1, 2, 3, 4, 5, 6. That means excluding bias, okay? Excluding bias and not bringing bias into picture. So 3 into 2 would be 6. So you'll have 6 connections. In that way, if you have NV into H, how many connections will we have? NV into H. These many connections or weights your model is going to learn. Then say you're supplying it to the output layer. What will the output layer size be? V. You'll have all the 172,000 words because English vocabulary has approximately 172,000 words. You'll have all of those here. And you'll have output for each and every word. And that output would be probability because you are applying softmax. The job of softmax activation function is to take all the numbers and convert those numbers into probability values. And when you look at the connections, number of connections here, V into H connections would be there. Okay, so I'll just erase this because you understood one hot encoding part. It's erasing to ensure that there is less of this kind of scribbling on the screen. Now, overall, how many weights do we have? Here we have n into h between these two, and between these two, it is v into h. So when it comes to MLP, you have n into vh plus vh. These are the number of connections, and this you can write it as n plus 1 into vh. You can deduce in this way. So the number of weights that your model is going to learn is much less than v raised to the power n. V raised to the power n means exponential. Here it is at least linear. But then, if you have a paragraph which says Spain and France went on a war, which happens to be the first, say, paragraph, and somewhere it says the two countries, then here also you are not storing all the words in the memory. Since you are not storing all the previous words in memory, the no context problem still arises. No context is still a problem. And similar to traditional models, there is another problem here. If you build a model wherein you have 3 words, and if you want to predict the 4th word, that's it. It will work only in that context. That's called as fixed window context. If you have 4 words and if you want to predict the 5th word, it doesn't work. You need to build a different model altogether for that. Or if you have 2 words and if you want to predict a single word, once again, it doesn't work. Okay, so things work only in fixed window of context. If you have 2 words and if you want to predict the 3rd word, you build a different multi-layered perceptron altogether. So each time, and English text, right? You might have 2 words, 3 words, 4 words, 5 words. You can have 1,000 words also. So each time if you keep building your model, then the number of models will increase and it will be too complicated. So people thought, okay, traditional language models had certain issues. When we try to fix that using neural networks, MLP, that also is having certain issues. That is, previous words are not saved in the context, and you also need to be satisfied with the fixed window of context. Now what? Now people thought, okay, let's look into altogether a different architecture. And they moved on to something called as recurrent neural network, RNN. And here they try to solve these 2 issues, no context issues, memory issues, and all that. But let's understand how it works. The first layer would be a dummy hidden layer, just for the algorithm to get started. All the values will have zeros here. So it's a dummy. Say you have 3 words, and if you're trying to predict the 4th word, then what happens? For now, I'll just remove these. I'll just remove these for now. So you're giving word 1, first word as an input to the hidden layer. The size of this will be V, because any word, you need to convert it into number format. You cannot give the words as is to your model. So what do? You perform, say, 1 hot encoding, and you give that 1 hot encoding as an input. V, vocabulary size. And then say you have a hidden layer H. Here you'll have 172,000, and here you have whatever hidden units you give, right? If it is 4 by 4, then the number of connections will be 16, 4 into 4. Excluding bias. I'm not considering bias. Of course, you also need to include bias. But for our ease of understanding, I'm excluding bias. So the number of weights here will be V into H. Then H into H will be the weights here. 4 means 16 in that, right? Now say you're supplying the second word to the algorithm. That will also have a vocabulary size V, and say you have hidden layer which has H units. Then the number of weights will be V into H. And here when you multiply these two, you get H into H. And then again, say the vocabulary size is V, number of hidden layers is H, then again you'll have V into H, and then H into H. And say you want to predict what will be the fourth word. So in your output layer, you're going to have V neurons, 172,000 odd neurons. And then you'll get the probabilities pertaining to each and every neuron. For each and every word, for that case, you'll have the probability values. And you'll pick the one which has the highest probability. And you say, given these three words, this should be the fourth word. Automatically, you're predicting that. And the fourth word would be that word which has the highest probability. And why do you get probability values? Because we use softmax as an activation function. So here also, the number of weights will be V into H. Or H into V, however you call it. Okay? Now, this V into H will be different. This V into H will be different. It depends on the number of hidden layers you have, etc. When this word gets into the hidden layer, this calculation happens and it is moving forward. The word, word one, information, is moving forward into the second unit of RNN. So this is word two. When you supply word two as an input, word one is also coming alongside. Now the output that goes here will contain both information of word one and word two. Then when you supply word three, you're also supplying from here word one and word two, and here word three. So all the previous words are getting carried forward. Information of that is getting carried forward. It's not getting missed out. So the problem of no context, which was with traditional and MLP, is solved. So now you have the words, and the previous words are saved in memory, and the context is maintained. Next, you calculate the, say, fourth word should have been amazing, but incorrectly it was predicted as some other word, as disgusting, for example. Disgusting word was predicted, but actual word in your corpus was amazing. So there will be a loss. Since there will be a loss, you again backpropagate and update the weights. Every algorithm of neural network works in a similar fashion, friends. Move forward, calculate the loss, backpropagate, update the weights. And why are you going to update the weights? You're going to update the weights to minimize the loss. Okay, this is how it works. Then, when it backpropagates, all the weights are updated. But let's see. Here we have VH, VH, VH. And here you have HH, HH, HH. And here also you have VH. If you have N words, you'll have N into VH plus. Since you have N words, you'll have N into HH, number of weights. Plus for this output, you have VH. Since you have N words, you'll have N into VH. If I were to compress this, if I take these two together, become N plus 1 into VH plus N into HH. If you look at the number of weights of your MLP, it is N plus 1 into VH. Here you have N plus 1 into H plus additional weights. So the number of weights are more in RNN. Hold on. But what happens here is, after you backpropagate and update the weights, you take an average of all these weights and replace all these weights with the same set of weights. So all these will have the same weights. So here, instead of NHH, it will become HH because 1 into HH. All these weights, VH. You take average of all these weights and you get one set of weights. You replace all of these with the same weights. So N will become 1. 1 plus 1 is 2. So it becomes 2VH. So the number of weights also would significantly come down. And you'll have 2VH plus HH. So the number of weights have come down significantly and the previous words are getting stored in memory. Okay. Then people use RNN model for image captioning also. That means you first take your image, pass it to your CNN network. So you'll have image, pass it to your convolution layers. And then whatever output you get here, right? Take those outputs and supply it to RNN model. And say your goal is to do image captioning. Give a caption to the image. If you want to give a caption to the image, such as the person in the video is running. The person in the video is running. So when it comes to RNN, right, when you give each probably input to your RNN, it will take that input and immediately it will predict. Immediately it will give you the prediction that the person in the video is running. In that way, it will give the output there itself. So you need not have a separate output here. So depending on the kind of business problem that you try to solve, you will either do the prediction as and how you give the input, or you will wait to process all the inputs and then take the, and then come up with the output. Here in MLP, there was, and in this also in traditional model, there was fixed window context, meaning 3 words. And if you want to predict 4th word, it will work only in that context. But here in RNN, if you have 2 words and if you want to predict the 3rd word, this RNN unit will collapse. You'll only have this part. If you have 4 words and if you want to predict the 5th word, this RNN will expand. So your RNN will expand if you have more words and it will collapse if you have less words. So it can work on any context of window size. So that's yet another advantage that we have, right? So because of all these advantages which RNN has, people started pursuing recurrent neural network to deal with sequence data as well as textual data. Textual data is usually sequence. So when you have time series kind of business problems, then also you can use RNN models. Okay. So yeah, the same thing is explained here. The symbol here means recurrent, meaning that word that is being learned, you're not throwing it away, you're storing it in the memory. That is what it means. So here, if you observe carefully what's happening. Okay, let me give the same architecture so that you don't get confused. This is what we want, right? Okay, now, XT means the current word. Let's say we are here XT. XT plus 1 means the next word. xt minus 1 means the previous word, xt minus 2 means the word before, xt plus 2 means the word after. So in that way, we'll talk about this xt. When you talk about xt, this will become ht minus 1, this will become ht, this is ht plus 1. So you take the number of weights between these two, right, into ht minus 1 plus, you look at the number of weights between this x and h into the current word. Okay. So whenever you have neurons here, you'll have integration component first, and that's this integration component. This into this plus you'll have weights here, hx, which is weight between these two, into this. When you multiply, do a sum product, you get the summation. But then you need to pass it to the integration function. Say you're using sigmoid activation function. We'll go to this. Now let me say that this is a final thing. And then you need an output as well, which has h hidden layers. And the weights here will be ws. So ws into this would be the integration. There is no additional word coming because it's the output layer. And then when it comes to activation, since this is the final layer, you take softmax activation function if it is more than 2 categories. And finally, you get yt hat. So what is the probability that the next word will be one of the words in the vocabulary, given all the previous words, xt, t minus 1, t minus 2, all the way, right, would give you this prediction. That is what is written in the number format. That's the same thing. You can unfold throughout and you can fold throughout. If you have more words, you unfold, expand your RNN. If you have less words, you fold it. So that's what we do. The same explanation is given in a different representation format. Then the same thing is mentioned in, again, words also. For example, the initial hidden layer would have 0 magnitude vector, all zeros. Then you will have time period 0 until n minus 1. Okay. And then you do a forward propagation. This, keep forward propagating. And then towards the end, you look at the difference between the actual value and the predicted value, which will give you loss or error. Back propagate to update the weights. That's what is given. There's one disadvantage here, friends. If you keep on unfolding, and if the number of words are large, then what will happen? If the number of words are very large, that means if you have huge number of words, then when you multiply the weights with the hidden layers, when you keep multiplying the weights, right? What if the numbers are less than 1? The weights which are initialized are less than 1. Say you have 0.8. And then if you multiply it with, say, 0.7, you get a number which is going to be less than these two. And if you have number less than 1, once again, say 0.5, then it will come down further, right? You'll get 0.28. So the value keeps on decreasing. Eventually, this value becomes 0. Very soon, it will collapse to 0. That means if your weights are randomly initialized here, it will keep trying to, decrease the loss, minimize the loss. But if it gradient collapses to 0, your algorithm will stop. You had a chance of reaching the minima, but it didn't reach. This is called as vanishing gradient problem. Vanishing gradient problem. At the same time, if these values are bigger than 1, greater than 1, then what will happen? You say 1.1 into, say, 1.2, you get 1.32. Okay, 1.32 multiplied by another value which is greater than 1. You'll get a number which is going to be bigger than Please. So in this scenario, as and how your recurrent network unfolds, the value will keep on becoming bigger and bigger, and eventually it will go to a stage which is called as exploding gradient. In exploding gradient, what might happen is update, 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 and then it will jump like that. So you'll not get to the minima. Again, it might come here, again it might go. Again, it might come here, again it might go somewhere there. So that's called as exploding gradient problem. When you have vanishing gradient or exploding gradient problem, then people use something called as truncated BPTT, which is truncated back propagation through time. When you truncate, you say that do not unfold it for more than 10 times. If you have more than 10 words, don't unfold, truncate it. Only unfold it 10 times. Even if you have 20 words, just unfold it 10 times is what you'll see. So the advantage is that you'll not get into this vanishing or exploding gradient problem. However, the downside is that the complete set of words are not learned since you're truncating it. So your typical RNN also works based on backpropagation. It's called as backpropagation through time because you're backpropagating one word at a time. In that sequence, you're going back. So through time, you're going back. Truncated BPTT, we use when we have long sequence of words. Okay, that is when we go ahead with truncated BPTT. Then we use cross entropy, etc. for this purpose, and we have various other cases. Now, before I go to this, there is a question that one of our friend has, so I'll just unmute and then unmute our friend and then read this particular question. Yeah, Shri. Can you?
Hello, sir. Good morning.
Good morning, Shri.
Where else is the practical application of RNN apart from predicting the next word? I'm unable to understand. In day-to-day office or day-to-day life, where else can that be applied?
Okay. I am sure you watch movies and all that.
Yeah.
And in movies, you'll have transcripts which might come up.
Yes.
That is an example of this only.
Oh, okay. Okay.
It's not just prediction, Shri. We have to broaden our thought process wherein this is not just prediction. RNN can be used for giving you the sequence of words, given the images or videos, it can give you this. And a few people have given automatic commentary, in applications such as Cricinfo, etc. Today we have India-Pakistan match, so it makes sense to discuss that. Automatically giving that.
Okay.
And it can be used in dealing with sequence data. For example, say we are in a border location in defense.
Okay.
You are communicating with me that, you know what, there are intruders and something on those lines. Suddenly a few words weren't clear. So what will RNN do? It will look at the sequence of words. It will look at what is the probability that next word would have been intruders.
Okay.
As opposed to some other word.
Okay.
Right? This is yet another thing. It is used in automatic grading of the applications also. Like when you write GMAT, right? In the good old days, when I have taken, they used to send your essay to someone who would manually evaluate it and grade it. But nowadays they are using the applications where the application has already was already trained on Wikipedia kind of stuff and Wall Street journals, etc. So it has sufficient information about grammar. So it would quickly evaluate on those lines and automatically it will give you a score.
Okay.
Yeah, in this way there are thousands of them.
Okay. One more doubt I have. Can I ask?
Please go ahead. Please go ahead. Yeah.
Prediction of the fourth word based on the probability of the entire individual words. For example, if I'm writing a sentence on say marketing topic or finance topic, you showed that
See, I'm losing a few words of yours. 1 or 2 words is clear, then
okay.
remaining words I'm losing.
Is it better now? 1 second. Let me 1 second.
Yeah, sure. What happened, Shri? I think you need to accidentally let me unmute you.
Yeah, is it better now?
Yeah, it's better.
Yeah. See that prediction part which you explained, that after Wall, it will be automatically taken it as Wall Street
Yeah.
based on topic and context.
Yes.
So it will have an inbuilt library or inbuilt which will say that what is the probability of a particular word happening after say another word, right? That's what you explained.
Yeah. So here, first of all, your models will not automatically work. All these things are not automatically saved, right? So
Yeah.
you have to go and get the data.
Oh, okay. So I will have to make them learn whatever topic I'm researching or whatever topic I'm studying, for example. We should input all those words and everything that particular context before applying this through network.
Exactly. You could take the words from all these different forums, Financial Times, so on and so forth. You create your corpus.
Oh, I need to create.
Once you create your corpus, you train your model using recurrent neural network. And once you train your model on recurrent neural network, you can use it for real world applications, wherever you want to use it, right? For the next word prediction.
The training, the initial training part, which you told that, from various sources, that will be, running into, huge sites. We need to train them.
Absolutely. Yeah, absolutely.
Oh, okay.
It depends on you completely. If you say that I want complete Wikipedia, then probably it will be in terabytes, and then terabytes of data you need to process. Or if you feel that, you know what, I just want only artificial intelligence related articles from Wikipedia to be taken, size will be less. So it depends, right? Completely depends on your business problem. This is one. Okay. Second thing is, what people thought is, since it's going to be very costly affair to extract, to scrape all this data, to get a huge corpus and then train it, to train you need GPUs and TPUs and huge amount of compute, it'd be very costly affair. Hence what universities and various government organizations and governments for that case do is they give a research fund. Okay. And using that research fund, they purchase the hardware, huge hardware, etc., and they train the models. They train that and then keep it ready for you. You have to go figure out what are the trained models, and you just pick those. And picking those and using is called as pre-trained models.
Oh, okay.
Okay. When you use pre-trained models, it's called as transfer learning. So the knowledge of something else is being used for some other purpose. Okay,
like the stop words dictionary, what it is available in open source. There will be the learnings, this transfer model of marketing and specific topics available.
Different models. Okay, I think I'll have to explain you here one more thing. Okay, so how transfer learning works? Let me tell you. If I take an image tree and I supply it to the first hidden layer, what do the first set of hidden layers capture? Low level details.
Low level details, yeah.
Wonderful. Low level details, one example that I can give is pixels. Whether I take an image pertaining to a cat or whether I take a tumor radiology image, both the images will have pixels, correct?
Yes.
So whatever is already learned as part of the initial hidden layer, I can use it and apply on any data on the planet.
Okay, low level
data, literally. Yes.
Okay.
Next set of hidden layers will capture what? Mid-level details.
Mid-level and
Mid-level means if it's a cat will have an eye. This will be having circles. Here, tumor also, when you look at tumor images, will have some kind of circles. So I can also use a mid-level then.
Okay.
If even though I train the model on cat images, I can supply the tumor images also, because the initial set of hidden layers captured low level and mid-level details, which will be the same given any image on the planet. The only thing that will change is the high level. So I will take all these weights. I'll not train them. They're already trained. I'll just take those weights and I'm going to only train this part for my specific business problem.
Okay.
That's it.
Okay. So in this case,
you need not have marketing data or some other data, etc.
Okay.
Different models. You need not go about searching in that way until and unless your underlying corpus is 100% different.
Okay. Okay.
Say your regular English dictionary versus your medical dictionary. If you feel that they're two completely different things, then obviously the model which was trained on regular English dictionary cannot be used for medical purpose. You need to go figure out, do I have something which was already trained on medical dictionary? And you will have to reuse that. Like there are something called as BioBERT, BIOBART. So in BERT models, which are very advanced models, which are explained in our AI and deep learning stuff. There we talk about BioBERT. We talk about FinBERT. FinBERT is for finance. Financial terminologies. You would not find each one of that in your regular English dictionary, regular usage dictionaries. Right? So that will have a different corpus. So FinBERT is something which was trained on that.
Okay. So we need to select the appropriate dictionary in the CNN, trained model in the CNN before doing any prediction.
CNN or RNN or ANN. For everything we have pre-trained models.
Okay. Okay. Thank you, sir.
Yeah, sure. Okay. So when it comes to your CNN-RNN models, wherein you're trying to combine two different architectures, you take your image, supply to your CNN model, extract all the features, supply it to your RNN model. Within RNN model, the first thing would be called as start. Start means you're starting your algorithm now. Okay. So you reserve certain keywords only to indicate the start, and you reserve certain only to indicate the end. Okay. So you're starting. First word is straw. Whatever you get here, you supply it to the next neuron. Say you get hat. You take this hat and then you supply it once again. Then ultimately you get, whenever that is the image captioning starts, it ends it. And it says that for this image, the caption would be straw hat. Okay. So what you do is conf, pool, pool, conf. In that way, you'll have this entire part is called as convolutional base. And then whatever features you extract here, you supply it to your recurrent neural network. And that RNN would actually do the predictions and give you the end result. In that way, you can use it for image sentences. Here, Microsoft Coco dataset, the way the Coco dataset was designed was that it had 120,000 images. And for every image, say image 1, there were 5 sentences. So for this image 1, sentence 1. This is image 1. For image 2, for the same image 1, sentence 2. For the same image 1, sentence 3. For the same image 1, sentence 4. For the same image 1, sentence 5. In that way, we had sentences. And if you have 120,000 images, 120,000 into 5 would give you 600 different row items. And then people train the models. And then when you supply a new image, it will give you the caption, image caption. And then people observed that there were certain issues pertaining to RNN. For example, if we say Having said, I got my doubts clarified. Shri muted the audio. Assume this is a sentence. When you read this sentence, your regular RNN would read it left to right. Having said, I got my doubts clarified. In this way, when it reads, it will first encounter the word I. It doesn't know who this I is. And will just move on. And then it finds the word Shri, muted the audio. It will not be in a position to relate Shri to I because first this pronoun is coming into picture, then noun. Okay. But if you have bidirectional RNN, you can also read this sentence in the reverse sequence. Audio, the muted Shri. First, it is going to store Shri in context, then clarify doubts, my, got, I. So now it will look at what were the previous words we have seen Shri and this I. It is in close proximity. So probably I refers to Shri. In that way, it will capture this information, which otherwise would have been lost given you have used a typical RNN. So when you have bidirectional RNN, that is not the problem. But what happens is, since you are traversing in the forward direction also and in the backward direction also, the number of hidden layers will become double, and hence your network is going to consume twice the memory. Twice the memory will get captured. And we also have deep bidirectional RNN. When it comes to deep bidirectional RNN, instead of having depth equal to 1, you'll have multiple hidden layers. So the number of weights will just keep increasing. But the accuracy of the model also will keep increasing. So the good part is accuracy will increase. But the flip side is it will be very, very time consuming. It will take huge amount of time. That's the flip side. Okay. So those are a few things that one has to be aware of recurrent neural network. So let me download the Python code and we will solve this. Now, not this. Let me open. I doubt. Okay. We just need GPUs, and I need to fix that GPU issue on my system. It's all about version mismatch, friends. There is something called as CUDA, C-U-D-A, that you need to download, and there is something called as CUDNN, right? These kind of things we'll have to typically download. And then we have to look at, for this version of Anaconda, for this GPU that you have, these are the stable versions. So I actually don't have the patience to do that. It will take huge number of permutations and combinations to do so. Each time there's a version upgrade, I run into these issues. So I'm selecting GPU. And see. Hence, world is moving towards cloud because they feel that, fixing all these issues is not my cup of tea. Installing the right software and all that. Let me connect. I'll have to probably sit down. I'll have to uninstall everything and then install maybe. Then hopefully it will start working. RNN software. a pretty simple software. It should work seamlessly. Okay, so what are the various things that we are doing here? We are trying to import the required libraries like simple RNN, sequential model, embeddings. Embeddings are like one-hot encoding friends. You take your textual data, for instance, and what do you do? Here we are looking at Internet Movie Database reviews. Movie reviews. Okay, we are looking at movie reviews here. And we are taking the textual data, and textual data cannot be supplied as is to your recurrent neural network. So what are you doing? You're converting it into some vector format, vector of numbers, which is called as vectorization. In order to convert this into numbers, you can do one-hot encoding. But when you do one-hot encoding, there'll be a lot of zeros in it. In the table, you'll have a lot of zeros. Only one word will have one, rest all will be zeros, right? So it will have a lot of sparse data. There'll be a lot of sparsity. To counter this, people came up with another technique called as embeddings. Here you can define, for example, you can say, I want an embeddings of size 32. So what this does is, it will take every word, and every word would be represented using 32 numbers. Whereas if the same word has to be represented using one-hot encoding, what would have happened is the size of this would have been 172,000, because those are the number of approximate words in English dictionary. You'll have 172,000 words. Okay, that would be too cumbersome, right, to store. Whereas when you do embedding, every word will be given a unique number using maybe 32. If you give 32, if you say 64, using 64. If you say 100, using 100. So the size of the data reduces significantly, and instead of being sparse, this will be actually dense. So what we are doing is we are first importing all the required libraries. This is exactly what you need to do. And when you start working on projects, at the word go, you might not know what different libraries you need. Eventually, you will come to know. So put all these in one place and give an explanation after. Put a comment. Why are you importing this? Why are you importing this? So that you are clear as to why you actually need it in your algorithm. Then here we are creating a sequential model. We are adding an embedding layer to it. Embeddings will take your textual data, it will convert them into numbers. Then these numbers, you are again supplying it to your RNN. You have simple RNN, you have bidirectional RNN, we have deep bidirectional RNN. Here 32, here 10,000 means take maximum 10,000 words. Even if your corpus has 20,000 words, unique words, you want to take only 10,000 words. And each word should be represented using 32 numbers. And these 1,000 will be most frequently used words. If you have 20,000 words, you look at how many times each word appears, sort it, and then take only those words which appear maximum times. You can also look at the summary. Okay. Let me run this. Okay, so you have the data, number of parameters and the details. And next. Okay. When you say return underscore sequence is equal to true, here what you're doing is you're having 32 units. You're adding multiple RNNs, right? So let me tell you how it works. You are going to have a dummy hidden layer. Anyways, that is how it gets initialized. Then you have words. Every word is going to have 32 neurons, assume in that way, right? 32 neurons. And then you're connecting it to the simple RNN, which has again 32 neurons. When you say return underscore sequences is true, it will take this and the sequences it's going to return to the next layer. It will go on like this. The moment you stop return underscore sequences, that is where it will give you the output. If you don't use these, right, and if you still go ahead and define all these things, then it will print the results here, here, here. If you don't want the results to be printed immediately here, and instead, if you want to take these results and then finally you want to get an output, then you need to use return underscore sequences equal to true. Okay, the number of parameters are given. And then what we are doing here is, let me take this data separately. I'm just creating logical blocks. So here what we are doing is we are importing IMDb, Internet Movie Database. We are saying maximum I want only 10,000 reviews. Okay. And each review, each movie review, even if a specific movie review has say 1,000 words, someone has written a lengthy movie review has 1,000 words, you cut short it to 500 only. So you're saying you want 10,000. Okay, those are the maximum number of words that you want. Sorry, not reviews, my bad. Maximum number of words you want. And you're saying that take every movie review and ensure that every movie review has maximum 500 words. So say you have all the reviews, movie reviews. One movie review has 10,000 or 1,000 words. So it will remove these. Another movie review say is exactly 500 words. Fine. The third movie review has only 100 words. Then what will happen? You do padding. Padding means you all add zeros just to ensure that you make it 500 so that every word has a consistent size. Because in your neural network, you have to define how many neurons will you have in your input layer. And those many values should be supplied to your model. So you take these many words, 500 words, 500 words, 500 words, and you look at how many unique words are there out of all these things. Words which are, even if a specific word is repeated multiple times, amazing, 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 it be considered as one word. So in that way, take all those words and you might get, say, 20,000 words, unique words. You sort them in a sequence and then take the top 10,000 words. That means words which have been repeated maximum times. Okay. And when you process the data, you're saying that you want to process it using 32 words at one time. So that's the batch size that you're giving. You know about batch size. Right? Now, what are we doing? The sprint here, I think this is probably not needed. So here, let me run it. So when you run this, when you're trying to import, it is going to the Google APIs and then it's trying to pull the data for you. And then when you load the data, you're saying the maximum number of words should be only 10,000. I don't want more than those words. And then you are splitting that into training data, input and output, test data, inputs and output. Then you're printing the details here. Length of input data is you have 2,500 training sequences. So that goes as is. And here you're saying print the length of input data. You have 2,500 reviews. And then test sequences, whatever you give here will get printed as is. Then here you're saying print samples into sequences. And then here what you're doing is you're saying, let me sequence by padding the data of input training. And I want the maximum length to be 500. So that means if a specific review has more than 500 words, remove those. If a specific review has 500 words, keep it. If you have a specific review which has only 100 words, pad it. That is what it does. And then it's printing the results. It's saying that we have 2,500 reviews of 500 words, 2,500 reviews of 500 words. Then we are defining a model. We are first creating a we are first defining a sequential model and we are adding the layers. We are saying first embedding because you cannot supply the words as is. So you're taking each word, you're representing that using 32 numbers. Then you're adding a simple RNN with 32 neurons. Then you're adding one dense network. You're taking the input. You're having an embedding layer with 32 neurons. Okay. Max features is 10,000. So this will have 10,000 size. Then you're supplying it to simple RNN with 32 neurons. Then you're supplying it to 1 neuron in dense. Because maybe we want to classify given that review as whether that review is positive or negative. So if it's if it is a two-class problem, two-class classification problem, you'll have a single neuron and activation function would be sigmoid or tanh. And since you have binary data, right, two-class problem, we use the loss as binary cross entropy. And the metric that we want to monitor is accuracy. So first you define your model, the architecture, then compile the model, then fit the model. And you're storing the results in history. For our ease of understanding, let me store it as into another object as RNN model. Okay. So you're saying model.fit on the input data, training and output. You want 10 epochs, batch size is 128, and you also want to split the data at the same time. So you, from this training data, take 20% of the data, put it aside, and let's call it as validation data. Then you run it. So epochs are running. While epochs are running, I'll just change these things to RNN model. And it might take time. Let it take time. While it takes time, I'm going to explain the remaining code. Okay. While this happens, I would also try out one more thing. It is number of epochs is hyperparameter. You can define any number of hyperparameters. You can give any number of epochs. It's a hyperparameter. Okay, the second epoch is going, and roughly it is taking 1 minute. So this might take 10 minutes. Let me explain this code. So now what we will do is, for every step, you'll have the accuracy, which is a training accuracy, and you'll have validation accuracy. And also you have loss and validation loss. And all these for every epoch will get stored in this. Then when you go to RNN.history, all the accuracy values for all the 10 epochs, it's going to run 10 epochs now. For all these 10 epochs, the accuracy values will get, you're taking those and storing in those. All the validation accuracy for all the 10 epochs, which would be there in this RNN model, history, you take that and store it in this. Take the loss, which is training loss in RNN. Within history, you have the loss. Take it, save it here. Within this, in history, you'll have history of all the validation losses. Take those, save it. And then you're saying epochs should be, you want range of numbers to be printed. 1 until length of accuracy plus 1. How many accuracy values will have? If you run epoch 10 times, you'll have 10 accuracy values. 10 plus 1 is 11. Why are you taking 11? Because the last number is ignored. When you run range, you'll get 1 to 10. So if you want 1 until 10 because you have 10 epochs, then put 11 here because the last number is ignored in Python. Then you plot those. You try to compare training accuracy and validation accuracy across all the epochs. So on epochs, you'll have 1, 2, 3 until 10. And then you have accuracy, which will be in blue colored circles. You want to give a label as training accuracy. Validation accuracy, it's just going to be a blue line. You want to give a label, validation accuracy. You want to give the overall title to that plot. And that legend also you want to see. Legend means these labels will appear here, saying that blue color circle is training accuracy, blue color line is validation accuracy. Plot.figure will actually show you that figure. Okay. And not just that, for loss also you can see. Right. A plot.figure will open a new window. In that it is going to show you loss and validation loss. So what you're trying to do here is loss and validation loss. Loss would be in red color circles, validation loss in red color. You will have the labels also and epochs on x-axis. Y-axis you'll have loss for this line. For this line you'll have validation loss. Overall title. You want to see the legend also and see the plot. Okay. All right. Now we are in 5th epoch. Approximately 50 seconds is what it is taking per epoch. The more powerful your computer is, better it would be. Let me go to environment. Let me go to and wave. Let me see. I have that stable version somewhere listed down. If I can, GPU compatibility, probably this. This was the most compatible version, right? CUDA, I think I have 10.1. I mean, these are the various versions I downloaded for this GPU. NVIDIA GeForce GPUs. We have 2080 Ti that is being used by Sharath, I believe, for the project works and all that. So here 2.2.0, right? So let's download that. Let me create a new environment. Let me call it as deep learning. Let me go with Python, slightly older version. I don't know, maybe newer versions have issues. Maybe it's not compatible. That's why I'm just going with one version down. Here we come on. So it's creating an environment for me. So in this environment, do we have obviously in install you don't have, I don't see, TensorFlow. So let me go here and let me say, rather than pip install TensorFlow, let me say conda install TensorFlow -g. This would actually, what this particular function does is, it will look at what are the various softwares that you have, various versions you have, and it will try to install those versions which are compatible. Okay. So that's why, sometimes making use of Kunda might make sense. So it's loading the packages of this. This is how you typically fix the issues, right? Last time, I think Kuda toolkit Kuda toolkit, I believe, is probably 1 GB. You need to go to internet, download that. For NVIDIA, you need to download it. Okay, so these are the various things that have to be downloaded. It would take time if I do this, but yeah, fine, that's okay. So we have TensorFlow. Okay, 2.3.0, I think that would be the right version is what they're saying. But I have tried out 2.3.0 also. It didn't work out, I believe. Anyways, let's see. If it doesn't work out, if it still throws me error, then obviously my job will be to go and install the specific version. In this environment itself, we will install them. Let me see if it will be faster. While this is going on, what's the status here? Yeah, the final epoch is in progress. Yeah, this is also done, right? So here, accuracy values were increasing, decreasing because the error surface will be like that. Now, if I were to run this, you will have to see two. Yeah, there we go. So legend is there and validation accuracy is there. And if you see after the probably third epoch, the divergence is increasing. And here also, after the third epoch, the divergence is increasing. So you have training and validation accuracy, you have training and validation loss. Okay, so you will have to stop and retrain the model with 3 epochs, because after 3 epochs, the divergence is increasing in the sense the model is kind of overfitting. Accuracy, training accuracy is continuously increasing, whereas validation accuracy is decreasing. So after 3 epochs, your model is overfitting. Since your model is overfitting, you can do one of two things. Use the regularization techniques and see how much you can fix it. Or one of the regularization techniques is early stopping, meaning run it with more number of epochs. After a specific epoch, your model starts overfitting, stop there. And retrain your model with less number of epochs. Let's see here. Okay, seems like this installation is also completed, but here it is still going on. Okay, now I'll go here. Where do I have Spider? Let me install Spider as well in this new environment. I just want to show you on the speed, because here this 1080 Ti, the software that I have or the GPU version that I have is considered to be fairly okay, not great. Just about okay. Yeah, for training, for delivering the trainings, it's okay because we work on a smaller data set. Certainly this won't be sufficient to work on live projects. Also gone are the days wherein you keep purchasing new and new laptops with more powerful GPUs. People are switching towards cloud. So you take a decent enough laptop or computer, and on cloud, when you want to use, whenever you have a requirement of working on projects, increase the GPU. We have Google Pro Plus also. If you want a even more powerful GPU or TPU, you can pay more to Google. For maybe 2 hours, 3 hours, you can pay. Once the training is done, downgrade it. Move back to a free version. That's what I would strongly recommend. Bring your own cloud is becoming the new norm. Like bring your own computer or bring your own device, BYOD. Organizations were saying you need to get your own laptop, you need to get your own mobile. We're going to sync all the emails, etc., softwares on your laptop. In that way, now we have bring your own cloud. You'll have a cloud account. They will give you a laptop, connect to your cloud and work. That's it. That's becoming the new norm. Okay, so let the spider come up, and then meanwhile, while this comes up, I want to quickly tell you about the next steps. Today we will be, by noon we will be stopping. Okay, because of certain other health checks that I have. Next week we will have whole day session, and then we'll complete it. Next Saturday, Sunday would mark the end of the weekend batch training. So now we will talk about SVM, which is also one of the deep learning, or I would say not deep learning, it's one of the black box techniques. You have neural networks and SVM. We'll talk about SVM. We'll run the code. That part will be done. And we also have naive ways, wherein we discussed about theory, we need to do practicals. With this, all of our machine learning algorithms will be done. So we'll complete these two. After we complete those two, we will wind it up. Then next week, we'll have regression techniques. On Saturday, we will discuss about regression-based techniques. All the advanced regression techniques also I'm going to teach. It will be linear, logistic, count-based models, multinomial, and bunch of those. And then the next day, which will be on Sunday, we'll have forecasting models and survival analytics. With that, we'll mark the end. Okay, let me launch Spider quickly. Let me show you the speed at which it works. If it is faster, good for us. If not, it will be fast, certainly, provided the GPUs get enabled. I don't know whether this is going to fix the issue or not, but I would certainly want to give it a try. Okay. Seems like it is. Okay. So let me copy this. Paste it here. I think there are still issues, right? Certain softwares are not installed properly. Fine, that's okay. I'll fix it at a later point of time. Let me not waste your time. Okay. All right, friends. So people have joined for masterclass. I think you can wind up. And if you want, you can continue to attend. That's up to you. So the time is approximately 10:47. 11:05. We'll be back and take this discussion further. And after the break, we are going to talk about SVM, which is also a black box technique, and then naive ways. Thank you so much. Yeah, thank you, Ramesh.